So dear students, now let me discuss about superposition principle. Okay, and basically here we have discussed about superposition principle for electric field. Okay, superposition principle for electric. Now before discussing the superposition principle, let me discuss about linear system. Okay, linear system, because the superposition principle is well fitted for linear system. And what is actually mean by linear system? So in physics, most of the cases, or each and every cases, there is an effect, and whenever there is an effect, there is a cause. So there is a cause and there is effect. So suppose we have a system like this. Suppose this is a system, any system, and there is a cause. Okay, and due to this cause, there is an effect. There is an effect. Now, if this cause and effect are related by linear equation, linear algebraic equation, or by linear differential equation, then this system can be treated as a linear system. And for example, in electrostatic, we have the basic law of electrostatics. We have Gauss law. We'll discuss later on. There is divergence E equal to rho f. And here you can see this is a linear partial differential equation. There is divergence. This is a linear system. And you have already studied about a famous linear system, that is, whenever there is a system, there is a mass, suppose, and a force is acting on this particle, and this here force is a cause, and due to this force, acceleration will be produced. The acceleration, that is f by f, nothing but effect. So there is a cause and there is an effect. This cause and effect are related by this linear equation, that is f is to ma. This is also a linear system. And whenever there is a linear system, the superposition principle is well fitted. So what is superposition principle for linear system? If this is a system and there is more than one cause, if there is more than one cause, suppose one is C1, that is C2. So there will be different effect, one will be E1. So if it is the linear system, then obviously C1 plus C2 is equal to E1 plus C2. E1 plus C2. So this will hold good for linear system. Suppose there is a system, okay, mass M, two forces are acting on this system. One is F1 and the F2. And the acceleration due to F1 is A1 and due to F2 is A2. Then the resultant acceleration is A1. Now, when the superposition actually need, so if we cannot find the effect for individual cause, suppose we can't, suppose we can't find the E1 and E2 separately for C1 and C2. In that case, what we can do, we can just switch off this C2 and we can see the effect of C1 separately, that is E1, and then we can switch off C1 and we can see the effect E2 or C2, and then we can add this to effect E1 and E2, and that will be the final result, the final effect of the system. So for linear system, if there is more than one cause, then we can see each and every cause separately, and we can note the effect for each and every cause separately, and then we can add the all effects, and that will be the resultant effects of the system. And this is actually the superposition principle in general. But now here we want to apply the superposition principle for electric field, and I have already discussed the superposition principle for force also, and obviously we know that the superposition principle will also be hold good for electrostatic force also. We have discussed earlier. Now here what we are interested about, the electric field. Suppose there is n number of charge, it is q1, q2, q3 and qn, and we are interested about the field at this point. So we can find the field due to q1, q2, q3 and qn separately. So when we want to find out the field due to q1, and we are not interested about the field about these other charges. Okay, so what will be, let the electric field due to q1 is e1 separately, due to q2 is e2, due to q3 is e3, and the net electric field at this point E will be the vector sum of all these quantities. Where the sum means the vector quantity. So this is actually the superposition. Now this can be extended. Instead of discrete charge distribution, we can extend this for continuous charge distribution also. So if there is continuous charge distribution instead of q1, q2, q3, if there is a line charge something like this, now what we have to do? We have to take a small charge element dq. Then we have to find out the field at a particular point, that is dE. Then what we have to do? Then we have to integrate for E. We have to integrate for E. And this integration will depend on the geometrical shape of this charge, of this distribution of the charge. Okay, it may be line charge, so it will be line integration. When it will be surface charge, we have to take the double integration, surface integration. Sometimes we have to take triple integration, volume integration. So we will discuss in problems how this integration will be changed. But here it is sufficient to say that if there is a continuous charge distribution, we have to take a small dq. So we actually, for point charge there is q1, q2, q3, q4 separately, but for continuous charge distribution there is no separately charge, but we have to take dq, 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 which are equivalent to q1, q2, q3, and here each dq are identical, but here this may be different. Okay, but the ultimate thing is that we have to add up all the electric. Okay, so according to superposition principle, we can find out the electric field due to some individual charge or individual charge element, and then we can add for all this. Okay, all the we can find out the electric field for each and every one separately, then we can add up all this. Okay, so this is actually the superposition principle. Now let me apply one in problem for discrete charge distribution, and the next class I will discuss about the continuous charge distribution also. Okay, so read this. So four particles each having a charge q are placed on the four vertices of a regular pentagon. Suppose we have a regular pentagon. Okay, 1, 2, 3, 4 and 5. Okay. Regular pentagon. Okay. Regular pentagon A, B, C, D, E. The distance of each corner from the center is A. This is center. The distance of each corner is A. And the electric field at the center of the pentagon. Okay. So there are four charges. Okay. Suppose here is Q, here is Q, here is Q, and here is Q. Now if we put another charge here, if we put another charge, if we put another charge here Q, then what will happen? The net electric field here is 0, because this is their symmetry. So each and every, so the total electric field will cancel out. Okay, so this is the superposition principle actually. So the net electric field at this point will be 0 due to symmetry charge distribution. Now this point has no charge according to the question. This point has no charge. So how we can compensate this whole thing? If we placed a plus q charge here, then the total electric field at this point will be 0. Now we can put a negative charge here. A negative charge here. Okay. Let me put a negative charge minus same. Then what will happen? Due to this 1, 2, 3, 4 and 5, this 5, for this 5 charge, the net electric field at this point is 0. But due to this minus q charge, the electric field will be 0. And that will be 1 upon 4 by epsilon naught qy square, and that will be along this distribution. Now, what I actually have done here, so this is actually equivalent to the pentagon as given in question. Okay. So in question say that this pentagon, this point has no charge. This point charge or charges. So this, according to the question, this point has no charge. And if you see carefully this figure, this point also have no charge. So this plus q and minus q will cancel out. So this point is equivalent to 0 charge. But I have intentionally put here plus q and minus q so that we can solve the problem easily. Because if you compare this for this 5 positive charge, the net force here is 0. The only field that will be exist here to this minus q, that will be around this direction. So the electric field will be at this point 1 upon 4 pi qy square along this. So this is how this kinds of symmetry problem can be solved. Okay, it is not necessary that there will be pentagon, there will be hexagon also. Okay, but the process will be same. If one point is empty, then we can put there plus charge and equal minus charge. That will be equivalent to the empty charge. Okay, this is how we can apply the superposition principle for discrete charge distribution. And next class I will discuss about, I will solve more problem. Okay, for continuous charge distribution.